All right, today we're going to do lab 2, correct?
Right.
Okay, so what's first on the procedure there?
First on the procedure, we are going to be making 2 solutions. We're going to try to make the same solution 2 different ways. One way is the right way, one way is the wrong way. Purpose of this is to see what happens when we make it the wrong way.
All right, so what solutions of sodium chloride?
Sodium chloride. So we're going to make two 50 milliliter solutions of 60 grams per liter. You're going to need to do calculations to find out how much sodium chloride it is.
So, you're going to weigh it out for us then?
Yes.
All right, here's a weigh boat.
Get a spatula.
Oh, spatula.
Thank you. Use sodium chloride.
Okay, so I see you have your 2 masses of salt ready to go and your 2 graduated cylinders, right?
Right. So for this one, we're going to put in the sodium chloride first. Do that just like this. Make sure we get all the sodium chloride in there. So then we can do to make sure we get all of the sodium chloride. Take a little bit of water in a transfer pipette and drip it down the weigh boat. Get anything left over. Sodium chloride is good at going down, so we don't really need to worry about it so much. Other things you will.
Okay, and now, according to the procedure, you're filling it up to where?
50 milliliters.
To 50 milliliters.
It would probably be good to fill it up to about 30. Mix it around, get all the sodium chloride dissolved. And then we can finish up filling to 50 milliliters.
So you're making the one in step 3 here, correct?
Correct.
Okay, so this is the right way, right?
Right.
Step 3. Now in step 2, it says add 50 milliliters of water to the 100 milliliter graduate cylinder and then add the sodium chloride. So in step 3 here, we just add the water right to the 50 mils of water. You can fill this up to the top there with the dropper. We there?
A little more. Just about. There we go.
Okay.
Then we add
the sodium chloride and let it dissolve. So which one of these, the one on the right, you added the sodium chloride, dissolved it, and then filled it to 50, and the one on the left, you added the water and then added the sodium chloride. Which one of these is going to be more concentrated?
Well, we can see that this is actually 50 milliliters.
Uh-huh.
And this is around 52, 53 milliliters.
Okay.
So this is probably more concentrated.
And that's the right concentration,
That
right?
is the right concentration.
And how would we determine the concentration now of these 2 different solutions?
Well, we don't know that we weighed out 3 grams.
Uh-huh.
We weighed out a mass of sodium chloride.
Right?
For the right solution.
Uh-huh.
We can do the mass over the volume.
Okay.
That'll give us the concentration.
In grams per liter, or grams per milliliter.
Yes.
All right, so let's record your observations, right, and calculations in your notebook. Excellent, so we're done with part A1, right?
Right.
Okay, part A2.
So for part A2, we will be making 2 solutions of copper sulfate, one in molarity and then the other in percent by mass. So
All right, so the first one, it says, calculate how many grams of copper sulfate are required to make 50 milliliters of a 0.1 molar solution. All right, so to perform that calculation, what kinds of things do we have to keep in mind?
We have to keep in mind the volume that we're going to be working with and the molar mass of copper sulfate.
Where can we find the molar mass of copper sulfate?
It's usually on the bottles right here.
All right, so what is that number?
249.68 grams per mole.
So that's how many grams there are if I wanted to put 1 mole of copper sulfate into, or whatever, weigh out 1 mole of copper sulfate, right?
Right.
Now, this says it's not copper sulfate, right?
It says copper sulfate pentahydrate. That means there's 5 water molecules associating with the copper sulfate.
Okay. So it's different if I were to just be using straight copper sulfate than if I'm using copper sulfate pentahydrate, right?
Right. So if you didn't have the molar mass written on the bottle, you would have to take into account the 5 water molecules. Just add the molar mass of 5 water molecules to the molar mass of copper sulfate.
Okay, great. So, you're going to weigh out then the appropriate mass of copper sulfate to make a 0.1 molar solution, but you don't want a whole liter, right?
Right.
So if it was 0.1 moles, then how many was in a mole again?
249.68.
Okay, so if we wanted 0.1 moles, then it would just be 24.968 grams, but that would be for a liter, right?
Right.
So we take 24.968, and we don't want 1 liter, we want 0.05 liters, which is 50 mils, right?
Right.
So we can multiply that by 0.05, and that should tell us how many grams we need, correct?
Right.
All right, excellent. Now, the second one, the second calculation that we have to perform, calculate how many grams of copper sulfate are required to make a 1.1% solution and make the solution. This is a little more complex, correct?
A little. So, a 1.1% solution, that's 1.1 grams for every 100 milliliters. We're only dealing with 50 milliliters, so it's going to be about, what would that be, 0.55?
Yeah, half of 1.1.
Yeah, so 0.55 grams.
That's how many grams of copper sulfate we want, right?
Yes.
That's how many grams of copper sulfate. But we're dealing with copper sulfate pentahydrate. So if we measure out that mass of copper sulfate pentahydrate, we won't actually get that much copper sulfate. Is that correct?
That's correct.
All right, so we can set ourselves up a ratio, right?
Yep.
Maybe something like this. We could see that we want 1.1% solution. That means 1.1 grams for every 100 mils, 1.1 grams for every 100 milliliters. But we're not going to be making 100 milliliters. We're making 50 milliliters. So that would be 0.55 grams for every 50 milliliters. But that's 0.55 grams of copper sulfate. And we're not dealing with copper sulfate, right?
Right, we're dealing with copper sulfate pentahydrate.
Pentahydrate, which has a larger mass.
Yes.
We know we want 0.55 grams, and that's how much we would want if the mass was just the mass of copper sulfate, and the mass of copper sulfate is 159. So we could set up a ratio like this and find out how many grams, how much copper sulfate pentahydrate we'd have to weigh out, knowing that its mass is 269.68. All right, so from this type of calculation, you can determine how much mass of copper sulfate pentahydrate you have to weigh out so that you can get 1.1 grams for every 100 milliliters, right?
That's right.
Excellent. Okay, so it looks like you put your masses of copper sulfate into the graduated cylinders. You've filled it up to the appropriate volume. But what? You got to mix it now, right?
I do gotta mix it. See, this one's a little mixed.
Mm-hmm.
It's a lot more blue than this one.
Right.
But we need to,
Get them completely mixed. So what are some ways that you can mix it?
we can go over here,
Uh-huh.
take a piece of parafilm. This is parafilm, it's a very waxy. Cool substance.
Stretchy paper. Okay.
Paper, I guess.
Stretchy plastic. Kind of like
One of the
saran
greatest
wrap.
inventions ever.
All right, so you're taking it and you're gonna use it to seal up the top really good.
Seal up the top real good.
Okay.
Don't want to make a mess. Then we can shake it.
All right, excellent. So, and you have to make sure that you shake it until there's no more what?
Crystals on the bottom.
Yeah, you can peek through there and see if there's crystals, right?
Yeah.
Excellent. All right, so after they're completely dissolved, then what does it say to do? Step 3, submit samples of these solutions to your instructor to determine their actual concentration. So you walk over here to your instructor, right?
Right.
And we're going to take a little bit of it. Okay. All right, we're going to take a little bit. We're going to put it in the spectrophotometer, and then we're going to determine the concentration. Right, determine if it's right. And if it's right, we say, well done.
That is right.
And then you bring your second one over, and we do the same thing. Right?
Right.
All right, so now we're done with part 1B.
Yes.
Excellent. Okay, so we've just finished part A2. Now it's on to part A3. And we have some information there initially about how it can be very important that you don't waste any chemicals for a variety of reasons, one of which is cost, right? It's also important to learn how to measure out things quickly because anybody can follow a recipe. It's not whether you can follow a recipe, it's the time is always a factor in life. So, how long it takes you to do the following, all right? So, we're going to get a stopwatch, right? Stopwatches will be over here on this cart. Get a stopwatch, and we're going to time how long it takes you to do this, right? So, start the timer, weigh out 0.242 grams of copper sulfate, add 2 milliliters of water, and then stop the timer. And we don't need the solution to be completely mixed, right?
Right.
So we're just going to follow that recipe and then stop the timer.
Right.
Now the second one might be a little more confusing, so that's the one we're going to perform here. The first one's pretty straightforward. The second one says start the timer, weigh out any number of grams of copper sulfate between 0.121 and 0.484 grams, and then calculate how much water should be added by solving the ratio below there. Oh man, the lines got shifted in this. So, we'll get a weigh boat, correct?
Correct.
You still have a... All right, so we'll time you. Ready? So you're going to weigh out between 0.121 and 0.484, right?
Right.
So go ahead and put that on the balance. Tear it. Ready, set, start. Well, get your bottle open. And then we can start the clock. Ready, go. All right, so it's easier to weigh out 0.121 to 0.484 as opposed to exactly 0.242, right?
Right. A lot easier.
All right, so we have the mass, 0.249.
So,
0.249. So how do we manage that mass now?
can just take 0.249 divided by 0.121, and that should give us the number of milliliters we need to use.
Okay. So 0.249 divided by 0.121. We have to perform that calculation.
0.249 divided by 0.121 equals about
2.057. Okay, why don't you divide that by 3? All right, so 686 microliters. So you have to add 686 microliters 3 times, correct?
Correct.
So there's that. We need a tip. There we go. So that's an easy way to weigh out or measure out that much mass or volume. So we're going to add that much volume. 1, 2, 3. Very good. And then that would be time to stop the clock. Okay? So we'd have to stir that up and wait for it to dissolve. But we want to compare how long it takes to do that one to how long it takes to do this one. And the second one here, if you're careful with weighing it out, there'll be absolutely no waste. Whereas the first one, every time you go over 0.242, you have to make sure that you don't put that back into the bottle. You put it into a different container for maybe the next steps if it's necessary. All right, so we finished part A, 1, 2, and 3, and now we're on to part B, correct?
Correct.
All right, what do we do in part B?
We're simply making one solution of ethanol and water, making a 50% ethanol solution. We're not going to go about that any particular way. This is for your own benefit. Just take 25 milliliters of water, 25 milliliters of ethanol, mix them together, see what happens.
Okay, and we don't want to give away the surprise, right?
Right.
So we'll let them do that. And on the table, there should be alcohol for you to use, so this is where you'll get the alcohol. Now, excellent. Okay, so that will be part B. Now we're on to part C, the last part. What do we do here?
Here we're going to make a few solutions of ethanol, 20% solution, a 40% solution, 60%, and 80%. Then we're going to measure their density and make a plot of this density, of the densities of each solution. Then you're going to calculate, using the trend line that you get from that plot, the expected density of a 30% solution. Then you're going to make that solution and compare it to your calculated value.
Okay.
Finally, I'm going to give you an unknown solution, or your professor, teacher, is going to give you an unknown solution, and you're going to determine the concentration of that solution.
All right. So how do we make, like it says here, 10 milliliters of, let's start off with the 20% volume ethanol. How do we make 10 milliliters of that?
You would measure out 2 milliliters of ethanol, put that in something that can measure out 10 milliliters, and then fill that up to 10 milliliters.
Okay. So like our 10 milliliter volumetric flask, would that be good?
That would be perfect.
Let's see, where is it? We have one. There we go. So, what's that? Oh, that's only 5? Oh. Where's the 10?
Here.
Found one? Excellent. All right, so we have the 10 milliliter volumetric flask. You said put 2 milliliters of ethanol in there. Probably best to do that with a micropipette, right?
Right.
2 milliliters of ethanol, and then you just fill it up to the line with water, right?
Right.
Okay. And then,
After that's done, make sure it's shaken real good.
okay, why don't we do that really quick? So here we have some ethanol. Two mils of ethanol.
Then
Let's see, where's the dropper? Do we still have the dropper?
not quite. I think I threw that one away.
Okay. All right. Another dropper.
Use a dropper to do the last little bit.
Right to 10 mils, right?
Right.
Excellent. Then like you said, we need to mix well now, correct?
Right.
Now, how are we going to determine the density of this solution?
Like in the first lab, you should just take 1 milliliter. You can use a micropipette, pipette that out onto a weight boat on a scale, and measure that 4 times.
Okay. Find its mass,
per 1 milliliter.
compare that to the volume, and have the density. Excellent. So, we're going to determine the density of the 20% ethanol solution. Now, how would we make a 40% ethanol solution?
4 milliliters into a total of 10 milliliters.
Okay. All right, so we do that with the 20, the 40, the 60, and the 80% ethanol solution. We find their density, and then how would we plot that data on our Excel? Or how would we treat that data?
We would... Should we actually make it?
Yeah. So what is it we're going to be doing?
We're going to make a scatter graph, a lot like you did with your density of water and ethanol. This time though, the independent variable is going to be the concentration of ethanol. So the concentration of ethanol needs to be on the x-axis.
Okay.
Pull up Excel.
All right, so
we're going to do a 0%, 20%, 40%, 60%, and 80%. And because we know the density of 100%, we can throw that one in there too.
all right. So the density of the 0% solution is essentially the density of water because there's no alcohol in it, right?
Right.
Okay. So that's percent ethanol up there, or you're gonna? Okay.
Yeah. Well, make sure you label your graphs.
Okay.
Then
Density. And this one was about 0.998 for, that's what I got in my lab at least.
yes,
Is that okay?
that's what I got too.
Okay. 20%, let's say the 20% was about 0.965. Whoops,
Oh, not 965, 0.965.
for the 20% though, right?
Right.
And the 40%, 0.890. And the 60%, 0.850. And the 80%, 0.80. And the 70% or 100%, 0.776. Okay, so this is some possible numbers. You might not get those exact numbers. Those are just numbers that we made up based on our experience. So let's say, and you found all those densities of all those percentage of ethanol solutions, and now what do we do?
We highlight it, go insert, scatter graph, and we'll get a graph that we can make a linear, or get a linear fit trend line
Okay.
with that. So get a trend line, make sure it's linear, make sure we have the equation displayed on the chart.
All right. Now, how is that equation going to be helpful to us? Why do we want an equation here?
remember that the percent ethanol is on the x-axis. So for the 30% ethanol,
What do you mean the 30%?
the calculated 30% ethanol that you're supposed to find.
Oh, yes. It says from the data in step 2, predict what the density of 30% ethanol solution would be. Take 10 mils of 30% ethanol solution and determine its density. Make 10 mils of 30% ethanol solution and determine its density to test your hypothesis. Okay, so we can now predict the 30%. Would it be appropriate just to take 20 and 40 and find the average between them to predict the 30?
No. No, we have this formula. We should use it.
Okay.
Since we know that the percent ethanol is on the x-axis, we can just plug in 30% into x and solve for y.
Okay, so why don't you show them again how to label our axes so that we get a refresher on that.
Okay, make sure we go to Chart Tools and go there.
Okay.
And then over here.
Density in grams per mil, all right? Capital L.
Right.
Excellent. Okay. So, you're saying, oops, we lost our equation when we did that. Put it back in there. So you're saying that we can predict what the mass or the density of a 30% solution is by putting 30% into where?
Into x.
Okay. So if we put 30% into x, it'll tell us what the y value would be and thus what the density of that solution would be.
Right.
And then we're going to make the 30% solution, right?
Right.
And see how close we are.
Exactly.
All right, well, after we make that 30% solution, we'll be able to insert it right into here, correct?
Right.
All right, so let's say we predicted, or we did well, let's see, let's put it in here. What would it be? We can do that, right? By just making a little equation here and taking the value 30, right? Multiplying it by?
Negative 0.0024 and adding 0.9973.
Okay. Okay, so it predicted it would be 0.9253. All right, so we put that in there, and it changed our line slightly, but that's all right. Now we don't put the predicted one in here, right?
Yeah.
We would actually put the one that